Hello everybody, this is Dr. Christopher White and welcome back to Metamorphism and Facies. Okay, so we had just spoken about the chemical processes that take place during metamorphism. Now let's have a think about the physical processes. Well, the first physical process is of course flattening. So if you have a mineral that's soft enough and you put it under sufficient pressure, it will naturally flatten, it will disc. So, obviously your mineral has to be weak enough for this to happen. So, something like a crystal of quartz will be far more resistant to this, so it'll be a very difficult process to achieve. But, you can do it if you have sufficient pressure. Now, arguably one of the most important processes during metamorphism is rotation. So, rotation simply occurs during the compression of a rock. You have lots and lots of randomly orientated minerals. However, as you begin to compress the rock, you will naturally force these minerals to align themselves parallel to each other. And the minerals will align themselves at 90 degrees to the direction in which they are being compressed. So, for instance, if we compress these minerals from this side and this side, they will naturally align in this pattern. The final type of physical metamorphism that we get here is shearing. And obviously, as we know by now, shearing zone, we have essentially we have a piece of rock that's being stretched. So what we'll see in this situation is we'll see, clasts being drawn out essentially. This is a very common process essentially down in the lower crust, where the rocks tend to be far more ductile, and therefore you can achieve this far more easily. Both flattening and shearing are more of a ductile process. If the rock tends to be a bit warmer, a bit softer, it's easier to achieve. In contrast, rotation, while rotation is both a ductile and also can happen in the upper and lower crust. It just depends on the amount of pressure. So just to give you some idea, of course, here we have a nice example. So here we have what appears to be, if I guessed, a granodiorite, and over here we have a gneiss. You can see, once again, we have in this case quite weak, but you can see they are there. You have these bands of darker minerals all running parallel to each other with these lighter bands in between. So what's the process that's actually causing minerals to align? Remember, in this case we're looking at rotation. So you can see this is our volume of rock when we're starting off, and you can see the crystals are all randomly orientated. However, as we begin to apply a pressure from the left and the right, we take our circle of rock and we turn it into an ellipse. And you can see what's happened here is by compressing the rock, we force these crystals to begin to align themselves all parallel with each other. And that's the process that's involved. It's simply a compressive process, and all the crystals begin to align parallel to each other. And this process is especially good when you have long, slender crystals like a pencil, okay, or crystals that have a large surface area, like this post-it note, but are quite thin, okay. Crystals that essentially have almost a paper-like shape to them. These crystals, when they are under compression, will just naturally begin to align themselves parallel to each other. Okay. Now, obviously, you can't do this with minerals that tend to form, relatively random or rounded crystals. Something like quartz or calcite will obviously not do this because they don't have crystals that are long and slender, and they don't form crystals that are broad and flat. So now let's think about some metamorphic rocks. Well, metamorphic rocks come in two varieties, and we've discussed this term already, foliated. So foliation is simply when the minerals in the rock are aligned, producing distinct layers. Okay, so in some cases the foliation can actually separate the minerals into distinct colour bands, as we can see with this picture of some gneiss here. And we get different types of foliation depending on the different grades of metamorphism. Then we have a class of rocks called non-foliated rocks, and you'll be shocked to hear that non-foliated rocks do not have aligned minerals, and therefore they do not have a layering to them. Now, non-foliated rocks tend to occur in they tend to be more associated with upper crustal environments where the pressure is a bit lower, and they tend to be associated with contact metamorphism. In the case of non-foliated rocks, we assume that the stress is uniform, so it's coming from all directions. Okay, so that's consistent with being in the upper crust. From a geologic point of view, I know the pressure would be very high, 8 kilometers down, but from a geologic point of view, the pressure is relatively even in all directions in that environment. The same also goes down in the mantle. So during subduction, when that piece of oceanic crust makes it down into the mantle and it's being metamorphosed down there, because the pressure is relatively equal in all directions, you're actually going to produce a rock that doesn't have a foliation. It's a type of rock called an eclogite, and we'll discuss it towards the end of this lecture. So non-foliated rocks are associated with uniform stress fields. They are most commonly associated with higher crustal environments and very commonly associated with contact metamorphism. And some non-foliated rocks are simply altered parent rocks. So it's not uncommon for the most common non-foliated rock is of course marble, which is exactly the same as the parent rock, limestone. It's just the chemical composition hasn't really varied that much. All that's happened is you've taken lots and lots of very fine crystals and you've condensed them into fewer but larger crystals. Okay. So contact metamorphism will produce non-foliated rocks, and examples of non-foliated rocks are rocks like quartzite, marble, hornfels, but there are a couple more we'll discuss. And then we have regional metamorphism will produce foliated rocks because there's pressure. Okay, it's that compressive force which helps to drive the alignment of the minerals. And so foliated rocks will include rocks like slate, phyllite, schist, and gneiss. And once again, we'll discuss those as we go along. Subduction metamorphism, well, once again, we have that pressure that's going to force minerals to align. So we are going to end up with foliated rocks up in this portion. Okay. However, once your rock gets down here, well, you're down in the mantle and the pressure is relatively equal from all directions. So your rocks are not going to be foliated once they're down in the mantle. Okay. So let's think about rock textures. When we talk about the metamorphism of rocks, we primarily are talking about the metamorphism of two types of rock. Rocks that contain lots of clay minerals and basalts. Now, the reason for that is there are lots and lots of rocks that you can put under increasing pressure and temperature and they will do nothing. So for instance, we've discussed it already, a piece of granite. It's a very robust rock. It can take increasing pressures and temperatures for a very long time, so it doesn't metamorphose easily. So what that means is when you want to talk about metamorphism, you want to talk about the gradational changes from low temperature to moderate temperature to high temperature, you need some rocks which will actually begin to change at low temperature. And the most common types of rock that will begin to alter at lower temperatures are basalt and clay-rich rocks. And so what you're going to hear me talk about is primarily the metamorphism of clay-rich rocks and basalts. Other rocks might creep in every once in a while, but most of what we're going to talk about is based on those two rocks exclusively. Okay, so we're going to start up here with the foliated rocks. So slate, phyllite, schist, gneiss, and migmatite. Okay, so there are three common types of foliation, and they're each named after the type of metamorphic rock in which they occur. So we have slaty cleavage, schistosity, and gneissic foliation. So a slaty cleavage is produced by the alignment of clay minerals. We've just taken our mudstone, compressed it, and made all the clay minerals align. It's a physical process. Schistosity is produced by the alignment of mica minerals. So by the time we form a rock called a schist, the clay minerals have become unstable and they've broken down to form mica minerals. So we have recrystallization going on. Now the thing is because the rock is under pressure as it's recrystallizing, as the mica crystals grow, they all grow parallel to each other at 90 degrees to the direction in which the rock is being compressed. Okay, so during recrystallization, the mica crystals all grow parallel to each other due to the fact the rock is being compressed. And finally, we have a gneissic foliation, and that's when our rock separates into the light and dark bands. And we discussed that's a question of remobilization, and that's a little bit more difficult to explain. Obviously, once again though, the bands that form in the gneiss, well, they will tend to form at 90 degrees to the direction in which the rock is being squished. Not always the case, but most of the time they will. So here are examples of the different types of foliation. We obviously have a slaty cleavage here. You can see this rock is made of clay minerals. It's grey, it's quite dull looking, but you can quite clearly see the layering there, the foliation. Here we have a piece of schist. This rock is made of mica. Now this isn't a particularly great sample, I'm going to be honest, but it's what we've got, so let's work with it. But you can see just about, especially down here, you can see the layering the rock has. And then over here we have ourselves a gneissic foliation. You can quite clearly see these light and dark bands all running parallel to each other. So if a metamorphic rock has distinct layering, but is not one of these three options, we simply describe it as foliated. Now, when we're talking about the metamorphism of sedimentary rocks, the sedimentary rocks dominated by quartz or calcite do not undergo substantial change, because those two minerals are relatively stable under a high range of temperatures and pressures. So things like a very clean sandstone or a limestone, they're pretty robust during metamorphism. Now, this means that when we metamorphose a sandstone, it simply becomes a rock called a quartzite. Okay, it's like a sandstone, but typically what happens is the quartz grains get forced together a little bit under pressure, and the gaps in between them get filled in by quartz, and it produces this rather homogeneous looking quartz-rich rock. Limestone, on the other hand, will become a marble. We've already touched on this, so the limestone will be heated up. It will typically drive off impurities, so the colour of the rock will tend to become lighter, and it will also cause lots of small crystals to begin to coalesce to form fewer larger crystals. So marbles tend to be a lot coarser and a lot lighter in colour than your average limestone. Now, if your rock has mud in it, so it has clay minerals, this is where you can start forming alignments. Now, clay minerals have a shape like this post-it. Okay, they are quite broad, so they're very flat, but they're very thin. So they're like a piece of paper. So as we begin to compress them, they will naturally start to rotate and orientate themselves parallel to each other at 90 degrees to the direction in which the rock is being compressed. So these clay minerals will actually orientate themselves, and they'll form a clay-rich rock with a foliation which we refer to as a slate. As we've discussed, as the temperature begins to increase, the clay minerals become unstable. They will change to schists, and as the clay minerals recrystallize, well, the micas that form will also grow at 90 degrees to the direction in which the rock is being compressed, so that will produce a schistosity. There is an intermediate rock between slate and schist, which is called a phyllite. A phyllite essentially looks like a slate, so it's kind of grey and a bit dull, but it tends to have a slightly shiny look to it, because what you're seeing is you are seeing the mica crystals just starting to form. And if you remember from the minerals section of the course, you will remember that micas have a very, very high reflectivity. And so what you're seeing is you're seeing these very small crystals of mica reflecting the light, essentially making the rock look very, making the rock so it looks like it's essentially wet almost, but a little bit shiny. And of course, the final and most extreme version of a foliated rock will be a gneiss. So you can see them all here: slate, phyllite, schist, gneiss. So you can see the change in grade: low grade, low to medium, medium, high, and you can see what is going on there in terms of the minerals, but we've already discussed that. Now, in terms of the distribution of these particular types of rock, what metamorphic facies do they occur in? Well, shale is obviously going to be the protolith. Slates are going to start forming, typically as you just start to move between the zeolite and greenschist facies, but slates won't exist very long, because as you increase the temperature, the clay minerals will begin to break down pretty quickly to mica, so you'll start seeing a phyllite forming pretty quickly. And then the clay minerals will eventually disappear, giving us a mica schist, it's called. and then eventually we'll go from a mica schist to a gneiss. So you can see slates and phyllites tend to be more associated with green schist facies, so lowish grade metamorphism. Mica schists tend to be associated with amphibolite facies, so more moderate grade metamorphism, and gneisses tend to be associated with kind of very high amphibolite to low granulite facies, so relatively high grade metamorphism. So we've already discussed essentially this diagram, we've already seen it, but we know that obviously we're not going to get foliated rocks up here because the pressure is not sufficient. So essentially contact metamorphic rocks, no foliation, but we do know that in these areas where we have high pressure, this is where we're going to see foliation. So regional and subduction zone metamorphism, we are going to get foliated rocks. Now, gneiss is a very common metamorphic rock, but it's not exclusively formed by the metamorphism of a sedimentary protolith. Okay, so I've spoken about gneiss and I've included it in the kind of sequence of rocks that we get when we metamorphose a muddy sedimentary rock. So this slate, phyllite, schist, gneiss sequence. But gneissic rocks don't always form from muddy sediments. You can make a gneiss from a range of other common crustal rocks. The classic example, are quite feldspar-rich igneous rocks like granodiorites, diorites, and granites. Okay, so you can make them very easily from those kind of rocks as well. Now, the type of rock that you definitely can't make a gneiss from is a sandstone or a carbonate rock. So something like a dolostone or a limestone. You're not going to be able to make a gneiss from those. Now, this means that if you find a gneiss, you cannot be certain what the protolith is. Okay, so just bear that in mind. You can't be sure. Now, some geologists do feel that if you look at a gneiss and it contains less mica, that's an indicator that it's less likely to be of a sedimentary origin. It might be more igneous, possibly from a granite. However, that's not really a rule that I hold particularly in particular high regard. So, you can argue about that one if you want. So, in terms of rocks themselves, so here's our shale, and I do apologize, I've got to scratch my nose. Here's our shale, and you can see all we have to do is we have to force the clay minerals essentially to align simply by physical compaction. And we make them align and we end up with our slate. Now, as we begin to increase the temperature and pressure, the clay minerals begin to turn into micas. So we end up with a kind of a slaty rock that gets quite shiny looking. That's our phyllite. And then eventually the clay minerals turn completely into micas, at which point we have ourselves a schist. Now, in terms of the gneiss, on the other hand, well, gneisses can form from shales. But they can also form from, felsic igneous rocks like granodiorites here. And you can see all you have to do is you have to take these biotite crystals and, remobilize them to form these bands. Now, obviously, we've discussed the process of remobilization is somewhat complicated. But, once you've achieved it, you end up with a rock that looks like this. Okay. Now, the thing is this kind of rock is going to be very, very robust from a metamorphism point of view. So your granodiorite is mostly going to sit there. So, you take it to low-grade metamorphism, medium-grade metamorphism, nothing's going to happen. Your granodiorite isn't really going to start metamorphosing until high-grade. Your shale, on the other hand, will start metamorphosing at very, very low metamorphic grades because clay minerals, by their very nature, are very unstable at lower temperatures, even at lower temperatures. Okay. So our question then becomes, well, what happens if we keep ramping our temperature past that of a gneiss? Okay, so we've taken our slate, we've taken our shale, we've turned it into a slate, which is a clay-rich rock with a foliation, a layering, so a slaty cleavage, should I say? So we forced all the clay minerals to align parallel to each other. We've then started to change those clay minerals into mica minerals. So we end up with a rock that looks a bit like a slate but has a slightly shiny appearance. That's our phyllite. So that's kind of low to medium grade. Then we start to take all the clay minerals and we metamorphose them. They recrystallize to give us mica crystals, normally muscovite but sometimes biotite. And they will also align. That will give us our slaty cleavage. So I do apologize, our schistosity. And then if we metamorphose further, the schist will eventually give way and form a gneiss. And so the final question becomes, what happens if we go beyond the gneiss? Well, if we go beyond the gneiss, we start getting rocks that look like this. Okay, so you can see it has the gneissic banding. The one thing you'll notice though is if we just go back a little bit, if we can find it, this is a wonderful example of gneiss. You can see you have these nice straight bands all running parallel to each other. That's what most gneisses look like. You'll notice though this gneiss here has this very, very convoluted appearance to it. It's folding. So this would suggest it's under quite high temperatures and the rock has become quite ductile. So this produces what we refer to as convoluted banding. So if we keep increasing the pressure and temperature, eventually the rock is going to start melting. And this is the grey area. Obviously there's going to be that region where we have a metamorphic rock, which is 100% solid, and we're looking to try and get it to a magma, essentially 100% liquid. And so we're going to have this region where the rock is kind of like partially melting, where it's going to have metamorphic attributes like a foliation, but it's also going to have some minerals in it beginning to become liquid. And this is this kind of grey area where a migmatite sits. So migmatites are essentially this rock that spans the divide between metamorphic and igneous. So if we look here, we can see we have a gneiss beginning to fail. So you can see the different layers, but you can also see the layering is becoming convoluted. It's becoming quite folded. It's becoming a little bit messy. All right, this is telling us our rock is hot. It's ductile, the layering is starting to become a little bit incoherent. Now, this is referred to as a migmatic gneiss. Now, as we begin to increase temperature and pressure even more, eventually the layering is going to start breaking down. And you can see by the time we're at this point, we've completely lost the layering altogether. You can see there are, some hints maybe of some layering in the rock here. You can just about kind of see it there and there. You can see a couple of bands running parallel to each other there. But you can see on the whole, any layering has completely disintegrated away. Now this is telling us our rock is in the process of melting. So this is a migmatite proper, this kind of rock that's straddling this, metamorphic and straddling the metamorphic and igneous fields. Okay, so what about non-foliated rocks? Well, we're going to think about marble, quartz, and hornfels. So, in terms of non-foliated rocks, mainly temperature driven, so mainly just due to recrystallization. Uniform stress field, so that means no foliation. And most of the time, well, the big two, marble and quartzite, they're simply altered parent rock. So you get a very quartz-rich sandstone, it turns into a very quartz-rich quartzite. You're not really lost anything. The chemical composition remains pretty much the same. Obviously, there's some change in the physical characteristics of the rock, but as a whole, it's pretty much exactly the same as the parent rock. Same with a marble. Now, hornfels are slightly different, so we'll come on to those when the time's right. Okay, so a quartz sandstone, when you metamorphose it, will give you a quartzite. Essentially, all that happens is you can see we have individual clasts which are visible in our sandstone. In the quartzite, on the other hand, we've lost that clarity, haven't we? Okay, it's a mixture of compaction, obviously forcing these crystals even more tightly together. Then, of course, we have pressure solution, which essentially forces the crystals to begin to merge into one another. And we've also discussed that when you have pressure solution, you will begin to form very small amounts, essentially, of quartz liquid, and that quartz liquid will migrate away from the contact where the crystals are being pushed together, and essentially it will crystallize small quartz crystals in open spaces. So what will happen is you're forcing all these quartz crystals together, all the space in between them will begin to fill with these very, very small quartz crystals, which are the results of this pressure solution. And eventually what you'll end up with is a rock that looks like this, 100% quartz, can't really make out individual crystals easily, and it's a very strong rock because the quartz crystals are really locked into each other. So from a physical point of view, it's very, very robust. Now you'll also notice that in terms of the rock, because it's quartz rich, you can pretty much metamorphose it to nearly any temperature you want. You have to take it pretty much to the melting point of quartz. Okay, that's when you'll destroy the rock. from the point when it starts to begin to metamorphose to that point where it melts, the only rock you're going to get is a quartzite. So in terms of recrystallization, at higher temperatures and pressures, minerals will begin to become unstable and they'll break down to form new minerals, which are stable at the new temperatures and pressures. So as these new minerals crystallize, they will often take on textures associated with their environment. The new crystals can sometimes become larger and more tightly packed. Now, in terms of the quartzite, the crystals don't tend to become larger, but they will become more tightly packed due to compaction and pressure solution and dissolution. So in the case of a marble, this is what we'll tend to see: larger crystals, and those crystals will tend to be far more packed into each other. Obviously, we won't see an alignment because the stress regime is equal in all directions. So in the case of a limestone, okay, so here's our protolith full of fossils. What we'll see is we'll see the fossils break down, because remember, all of these fossils are just made of pieces of shell, and the pieces of shell are made of very, very fine crystals of calcite. And so as we begin to increase the pressure and temperature in the rock, what happens is these fine crystals of calcite begin to merge into one another, producing larger crystals of calcite. So we'll lose things like the fossils as we metamorphose the rock, but numerous small crystals will merge into fewer larger crystals, and so we'll see a coarsening of the rock. The other thing we'll see is that as we start to lose the gaps in between, the crystals start to merge into one another and become, well, not merge into each other, lock into each other, should I say. You'll end up with a rock that's considerably stronger. So under normal circumstances, a marble will be far more robust than a limestone. So recrystallization is most common in rocks that form deeper than 10 to 15 kilometers below the surface, because typically recrystallization is driven by heat. The only time you tend to get recrystallization at the higher levels in the crust is when you have contact metamorphism, and obviously the magma heating up the rock. So here's a couple of examples. Here's a nice picture of a sandstone. We can see we have all these nice quartz crystals. The gaps in between are obviously filled by, indicated by the mineral calcite, as the cement sticking the quartz crystals together. And then we come to this situation. Here we have a picture of a quartzite. Now this one hasn't actually been compressed too much because there's fewer signs of pressure dissolution, but we can see, number one, the pressure has forced the crystals to begin to merge into one another. They haven't begun to dissolve into each other, but they're kind of locked in because of all that pressure. And you can also see we've started forming groups of smaller crystals. Now this is because when we do have pressure solution, we can just see a little bit of it here. That will produce a quartz liquid, and the quartz liquid will just migrate into space where it can find it, and it will begin to crystallize out as smaller quartz crystals. So we can see this happening there, filling in the void. So this is a kind of classic sandstone. This is a kind of classic quartzite, although I've got to be honest, this particular quartzite has not been compressed too much. It's been compressed to the point where the quartz crystals are beginning to lock into each other, but they haven't been compressed so far that they've begun to undergo pressure dissolution. They begin to merge into one another. Now in the case of marble, as we can see, marbles tend to be lighter in colour and far coarser than the limestone which they form from. That's a relatively common trait. Now what we'll tend to see when we look at a marble under the microscope, we'll tend to see lots and lots of relatively equal sized crystals. They'll often have a relatively circular kind of look to them, crudely circular. And so obviously as these crystals don't have that flat appearance or that long slender appearance, there's no way you could make them align, so you'll never get a foliated marble. Now sometimes if you do have contamination in the limestone, that contamination will appear as other minerals. So in this case you can see this particular limestone was quite muddy, and so as the rock has been heated up, the clay minerals have eventually reached a point where the clay minerals have actually formed diopside, which is essentially a pyroxene mineral. And so as a geologist I can say this limestone may well have reached granulite facies, because remember, granulite facies is when we start seeing pyroxene. So there's a good chance we reach granulite facies to end up forming this diopside. Now in terms of hornfels, hornfels is a rather interesting type of rock. So a hornfels is an unfoliated metamorphic rock. So there's no alignment. Once again, there's no foliation. Now, they're most commonly formed during contact metamorphism, where there's no stress, there's no principal stress, there's no squishing force. Now, Hornfels are typically made of ferromagnesium minerals, so they're often quite dark in colour. So rocks that tend to like to form Hornfels are any rock that has a dark colour to begin with. Okay, but in theory, you can form a Hornfels from nearly any type of rock, with the exception of a sandstone and a limestone. Okay, all you've got to do is take that rock and heat it up a little bit, and but also it not develop a foliation. So under that set of circumstances, you in theory could classify that rock as a Hornfels. So that's why we say a Hornfels can in theory form from any rock. Now, if we have a Hornfels that is typically quite mud rich or quite ferromagnesian in terms of forming from a basalt, we tend to get the following progression of minerals in our rock as we begin to increase the pressure and temperature. So especially when we try and metamorphose basalt in a environment where we do not have a differential stress, so there's not a compressive force from one direction, we'll tend to see, first of all, the lowest grade of Hornfels will be the albite epidote Hornfels. As we increase temperature, we end up with the hornblende Hornfels. Increase temperature further, we end up with the pyroxene Hornfels. Increase temperature even further, we end up in a sandonite. Okay, so we can see these changes simply by looking at these larger crystals that tend to form in the Hornfels. So I know in this case we can see we have crystals of what's a mineral called andalusite. So I know this Hornfels has gone to moderate to low high, so moderate to high grade metamorphic conditions. That's the kind of range that this rock has achieved. So albites can often only be separated from other fine-grained dark rocks, so rocks like basalt and rocks like greywacke. Typically, you can only separate them when you look down a microscope, or if you're lucky, if you can see some of these larger crystals here. So in terms of the metamorphism of igneous rocks, felsic igneous rocks tend to be quite resistant to metamorphism and will remain intact until they become a gneiss. Intermediate igneous rocks, well, they're quite rich in silicon, aluminum, that should say sodium, Na, and potassium, and they'll follow a similar path to a felsic rock. They'll be relatively stable, not much will happen to them, and they'll eventually start to metamorphose when you get to very high grades, and that's when they'll start turning into a gneiss. And then we have intermediate rocks that have a higher calcium, magnesium, and iron concentration. They'll tend to follow a path more like a mafic rock, like a basalt. Remember, basalt do metamorphose relatively easily. So these intermediate rocks with the higher calcium, magnesium, and iron concentration, so the darker coloured intermediate rocks, they may well begin to follow a path similar to that of a basalt. So you will begin to see them metamorphosing relatively early. You'll see the appearance of actinolite, chlorite, and epidote relatively early, then the appearance of hornblende, then finally the appearance of pyroxene. So in terms of mafic rocks, as I discussed, as we increase the pressure and temperature, we eventually start to form pre-minerals, chlorite, actinolite, and epidote. There's also feldspar and quartz in your rock, and the presence of these three minerals tells us that we have reached green schist facies. Now, when we have a basalt protolith that we metamorphose to produce a rock rich in chlorite, actinolite, and epidote, it forms a very distinct type of rock. It is called a green schist, and you'll be shocked to know a green schist is green in colour. So green schists and green stones are essentially the same type of rock. It's just to do with the amount of pressure. Now, chlorite is a mineral like a mica, so it's quite broad but quite thin, so it's paper-like. Actinolite is an amphibole. Oh, when I threw it on the floor. So amphiboles tend to have a shape like this, quite long, quite slender. So when you put enough pressure on a green schist, well, when you put enough pressure on a green stone, the chlorite and actinolite will begin to orientate themselves parallel to one another, and you will end up with a rock that has a foliation. That will be a green schist. if you metamorphose a basalt to low grade, under conditions where you do not have a principal stress, so that there's no stress forcing the crystals to align, you will not form a fabric, and in that case you will have a green stone. So it's the same rock, same chemistry, just this one has a foliation because the rock formed under pressure. This one does not have a foliation because it did not form under pressure. So as pressure and temperature increases, they become unstable, so we lose the chlorite, the actinolite and the epidote, and they are replaced by amphibole in the form of hornblende. Hornblende is quite a dark black mineral, and once again it will form a type of rock called an amphibolite. Amphibolites can be foliated because just like the actinolite, hornblende forms long slender crystals, so if you put them under enough pressure they will all orientate parallel to each other, and so you can end up with foliated amphibolites. However, you can also have amphibolites that formed under low pressure environments, so there's no principal stress, so the crystals do not align, and that will obviously be an unfoliated amphibolite. The final type of rock is a granulite, and granulites will typically have quite high temperature minerals, so you can expect to see pyroxene. The amphibole will be lost, the pyroxene will take over from it. You can get other things like quartz, feldspar and garnet in the rock. Now granulites can once again, they can have an appearance similar to a gneiss, or they can have no foliation at all. It just depends on whether the rock has been, has had a principal stress applied to it during its recrystallization. If it has, well, in that case, you can force the darker minerals to align crudely. In the case of a granulite, it's not a great layering, but you can do it. Or if it's not under principal stress, the crystals will just grow in whatever orientation they fancy. So in terms of the distribution, here's our basalt protolith. Green schists, well, obviously will occur in the green schist facies field. Amphibolites will occur in the amphibolite facies field, and granulites will occur in the granulite facies fields. I'm sure you're shocked by this. So, obviously, these are our standard metamorphic rocks, but there are a couple of other more interesting metamorphic rocks in the form of blue schists and eclogites. Oh, I should point out, by the way, so that slide's in the wrong place. Anyway, this is a standard looking amphibolite here. You can see we have the black hornblende, we have plagioclase, which is this creamy white mineral in between, and we typically have quite a lot of garnet, which is the red mineral. Now, as you can see, this rock is unfoliated, but you can, given enough pressure, make these hornblende crystals align, and you can end up with foliated amphibolites. In terms of the green stones and green schists, well, that's all down to the pressure once again. So here we have two green stones. You can see the green colour in all three samples, so it's a very obvious green colour. In this case, you can see the crystals are not aligned, so there's no foliation. In this case, you can see the alignment there. So this rock has formed under pressure, but the minerals in the rock are exactly the same. The green colour is produced by chlorite, actinolite and epidote. Finally, we have a granulite. So a granulite can sometimes look like a gneiss if it forms under pressure. However, sometimes it will have no layering whatsoever. So in this particular sample, you can see there is a very, very crude layering. You can just see a layer coming through here. You can kind of maybe see a coarse layer here, maybe some finer stuff up here. But this rock is going to be made mostly of quartz and feldspar, typically some garnet, and these darker layers will be dominated by pyroxene. Okay, so do you know what? It's been it's been over 30 minutes, so this is definitely time to stop. So once again, pause the video, walk around, glass of water, cup of tea, get a snack, come back when you're ready for part 4, which will take us to the end, and that's it.